would never imagine anything like this as related to electricity when he's flying his kite. But the electric lamp is about as familiar an object in your life as you can think of. So familiar, in fact, that usually you don't give it any thought at all. When a light bulb is placed in a suitable circuit and the switch is turned on, current will flow through the filament of the bulb, causing it to give off light. Everything you'll do with electrical equipment will be done to cause a current to flow, to control its amount, or to make it work. A typical electrical circuit, such as this doorbell circuit, has a source of current, in this case a dry cell. It has a path through which the current flows, provided by the wiring. It has a device called the load, which uses the current. In this circuit, it is the bell. The push button controls the flow of current. For many years, no one was able to explain what occurred in a wire that permitted it to carry a current. In each case, the wire looks just the same. As an explanation, the electron theory was developed. To understand it, it's important to know that all substances are composed of molecules, which in turn are made up of atoms. For example, water is composed of molecules. By means of electric current from the dry cells, water molecules may be separated over a period of time into atoms. The test tube on the left now contains atoms of hydrogen gas, and the one on the right contains atoms of oxygen gas. Here's a diagram of a hydrogen atom. It's the simplest of all the atoms and therefore a good subject to study. It consists of a nucleus which contains one proton and an electron which travels around the nucleus in an elliptical path, in much the same way that the moon travels around the Earth. The revolving electron is held in its path by the attraction of the proton in the nucleus. The proton has a positive charge of electricity, while the electron is negatively charged. Remember this. Unlike charges of electricity, always attract each other. Other atoms differ from the hydrogen atom in the number of protons and electrons. Here, for example, is a diagram of an atom of helium. Its nucleus contains positively charged protons whose charges are balanced by two electrons traveling around the nucleus. For convenience, the protons in the nucleus are shown massed together. This diagram represents an atom of oxygen, which has still more protons and electrons. The difference between any two elements is only the difference in the number and arrangement of their protons and electrons. Elements such as silver, that carry electric currents easily, have a small number of electrons in their outermost orbits. Silver has only one, copper only one, and aluminum has three. Here are three atoms shown together. When the electrons are not strongly held by the nucleus, they may get free and move from one atom to another as free electrons. If these free electrons are forced to move consistently in the same direction toward one end of the substance, a current is said to flow. Such a substance through which current flows easily is called a conductor. A flow of electrons rarely occurs for any length of time unless some force is exerted on them to force them to move. Such a force may be applied by a battery or cell and is called the electromotive force. That is the force that causes the electrons to move. You must be careful to note that a battery does not manufacture electrons. They are already present in all of the parts of the circuit. It merely pushes them out of its negative terminal and collects them again at its positive terminal. The action of a battery is similar to that of a pump. Here you would not expect water to flow through the hose and empty into the tank. Neither will electrons flow through this circuit. However, if you install a pump, water can be forced through the hose. In the same way, a battery will cause electrons to flow through the circuit. Perhaps a comparison will help you visualize electron motion. Imagine that each man in this line represents an electron. The man on the left moves one step closer to his neighbor. This man now moves over. The next man does the same, and the next, on down the line. The progress of each man, representing an electron, is very slow. But the speed of the wave, representing the speed with which the flow of electricity begins, is very rapid. In fact, it's about 186,000 miles a second. Electrons move about with ease in good conductors of electric current, such as silver or copper. But not all substances conduct current equally well. Some, such as nickel or tungsten, have a lower conductivity than that of silver or copper, and so are described as having greater resistance to current flow. Still other conductors offer even greater resistance. Examples are cast iron or nichrome. A general statement can be made that each substance has its own specific resistance. Three other factors affect the resistance of a conductor. First, its length. The longer it is, the greater its resistance, as shown by the dimness of the lamp. Second, its size. The larger the conductor, the less will be its resistance. With the smaller one, the light burns less brightly. Third, the temperature. When the temperature is increased, the resistance is usually increased. To control the amount of current flow in circuits, you will often need to control the amount of resistance in them. Material of high resistance value may be formed into a small rod and placed in a circuit to increase the resistance. As you probably know, it's called a resistor. A very common type is formed by winding fine wire on a spool. In certain non-metallic materials, such as glass or porcelain, the resistance is so great that practically no current is allowed to pass. Such a material is, of course, called an insulator. An electromotive force may be produced in several different ways. One of the most important is by a chemical means, as in cells and batteries. The simplest kind of cell has two metal plates, one of zinc and one of copper. When a solution of sulfuric acid is added, the cell is complete. A battery, of course, is usually several cells, each of which produces an electromotive force. The zinc dissolves in the sulfuric acid solution, which is called the electrolyte. Any cell which can be renewed merely by the replacement of the used-up metal electrode, or the electrolyte, is called a primary cell. The cells discussed so far are wet cells and contain liquids which limit their portability. The most convenient kind of primary cell is the so-called dry cell, which is actually a kind of wet cell with the moisture sealed inside its zinc electrode. In this cutaway model, you can see that the positive electrode is a carbon rod in the center of the can. The electrolyte is in the form of paste. The electromotive force, or EMF, of a dry cell is generally 1.5 volts. This is a secondary cell. It may be renewed by forcing electric current through it in the direction opposite to its discharge. This storage cell has lead plates in a solution of sulfuric acid. A standard storage battery is made up of several such cells connected in series. The EMF of a storage cell is about 2 volts. Another one of the important ways of producing electromotive force is by mechanical means, illustrated by this demonstration generator. It has a coil of wire, or a rotor coil, which rotates in the field of a magnet, cutting its magnetic lines of force and causing an electric current to flow through the coil. Generators are an important part of radial gear. This is a motor generator set with a motor which uses the ship's alternating current and runs 3 generators. The generators supply special voltages for this radio transmitter, a type installed on many ships. You will very likely work with gear similar to this when you are with the fleet.